Great, thank you. I want to thank the organizers for putting together this great conference and inviting me to speak. So yes, I'm going to talk about the cosmological constant appearing as an initial condition for Milne-like spacetimes. Okay, let me give a quick outline of what I'm going to talk about. So I'm just going to give a quick introduction to the cosmological constant and why we put it in the Einstein equations. Then I'll quickly review FLRW and Milne-like spacetimes. I'll show how lambda appears as an initial condition for Milne-like spacetimes. And then finally, I'll get to my main result, which is to show that the cosmological constant appears as an initial condition because of the geometry of Milne-like spacetimes. That is, and this is really what I'm talking about here is the geometry at the Big Bang of the boundary. We will see all this. I'll then talk about applications to inflationary theory. And then if there's time, I'll talk about some upcoming work on past asymptotically flat de Sitter spacetimes. This is joint work with Gazelle, Gesni Sijnani, and Jerome Quinton at the Perimeter Institute. And the point is that the whole story that I'm going to tell here for Milne-like spacetimes has an analogous story for essentially models that are flat de Sitter asymptotically towards the past. And so we will see all that. Okay, the cosmological constant. So here is the energy content of the universe. I think we're all familiar with this. 70% of the energy is dark energy, 25% or so is dark matter, and 5% is ordinary matter. We all know this, but I mean, I don't think we talk about it, right? We're kind of shy away of it. We most of the times when we talk about dark energy, we definitely don't talk about dark matter. And most of the time we solve the vacuum Einstein equation. So we don't even talk about this 5% here, right? But I think it's still good to talk about. So here is one of the recent pictures from the James Webb telescope. Right? And I like this picture just because, right? All the dots are galaxies. These are the dust. That was the 5% that we saw, right? The gravitational lensing that you see here is much stronger than it should be if the matter was just dust, right? So this is why we're confident in dark matter. And then the dark energy, I mean, you can't really tell in this picture here, but what it does is there's negative pressure and it's giving an accelerated expansion to these galaxies. So they're moving away from each other at an accelerated rate. And this is due to what the cosmological constant that we insert into the Einstein equations here. And I mean, I guess mathematically, the cosmological constant isn't, too much of a mystery, right? This is just right here. We just put it in the Einstein equations, but it's still, I think, interesting physically, or at least it's, physically, it's a mystery. Why does something like this have to appear in the Einstein equations? I'm not going to answer that question. I'm going to show something like this happening, but I just think it's still a mystery. Okay, FLRW and Milne-like spacetimes. Okay, so some quick definitions here. So a CK spacetime MG is a four-dimensional time-oriented Lorentzian manifold with the metric being in CK. A continuous spacetime is called the continuous extension of a smooth spacetime. So MG is a smooth spacetime. This M extension, G extension here is the continuous extension. If you can find an isometric embedding of MG into the extended spacetime, and all my spacetimes are four-dimensional, so I don't have to say the dimensional constraint, and such that the manifold is a proper subset. Okay, a future-directed time-like curve gamma in the extended spacetime is said to be future terminating for a point P on the boundary if its future endpoint is P and everything else lives inside the original manifold, the original spacetime, right? And then we define the future and past boundaries of M within the extended spacetime as the set of points where there's a future terminating time-like curve for P. That's the future boundary, and the past boundary would be the past analog of it. So I think a picture says 1,000 words. So here, this is just the extended spacetime. Here is just Minkowski spacetime. This shaded region here is the spacetime that we're considering, and then here, this would be points that would lie on the future boundary, right? Because you can find a time-like curve that ends there. These would be points on the past boundary. This vertical line here would coincide to points that are both in the future boundary and the past boundary. And this point P here would be a point that lies on the boundary, but it's neither a point on the future boundary nor is it a point on the past boundary. Okay, so FLRW spacetimes. So suppose M, so consider a spacetime given by this warp product here, right? The scale factor A, we're going to assume is smooth, and then to be an FLRW spacetime, you assume this Riemannian manifold here is a space form. That is a complete Riemannian manifold with constant sectional curvature. In that case, this is called an FLRW spacetime. It's named after Freeman, Lamar, Robinson, and Walker, who first studied these. The function a of t, the warping function, is called the scale factor. The co-moving observers are the integral curves of this vector field, right? They're actually, time-like geodesics, and physically they model the world lines of galaxies, stars, and dust, right, that make up the universe. But of course, they don't model radiation because radiation travels at the speed of light. This is just a definition. If the scale factor goes to 0 at some point tau equals 0, then we're just going to refer to it as the Big Bang. And then finally, if A of tau has this asymptotic form as you go to 0, and the space form is just a simply connected hyperbolic space, then Mg is called Milne-like. Okay. And then the theorem is this: if you are a Milne-like spacetime, then you emit a continuous extension, and this extension is really happening through the Big Bang. So this theorem is not too hard to see, right? You just write out the metric in these co-moving coordinates here, and then you introduce new coordinates, this little t and little r here, where b is defined as such. And then when you introduce these new coordinates, then the metric becomes conformal to Minkowski spacetime, right? And I mean, why are these called Milne-like spacetimes? Milne was the first person to do this, but he didn't do it for arbitrary hyperbolic FLRW spacetimes. He just did it for the case when the scale factor was equal to tau itself. And when the scale factor was equal to tau itself, then it isometrically embedded into the Minkowski spacetime. In that case, the conformal factor, that is in Milne's case, this conformal factor would have been 1, right? And you can actually see that because if A is tau, then this becomes e to the log, and that cancels, right? Okay, so the big point here is that if you're not tau, but you're asymptotically tau as you go to the Big Bang, then this conformal factor is going to approach a positive constant as tau goes to 0. And so since this is non-degenerate, right, this is a positive constant here at tau equals 0, you can extend through the Big Bang. And so the extension happens like this. So here are the tau equals constant hyperboloids, right? They foliate your hyperbolic space. And then as tau goes to 0, the hyperboloids, they foliate down to the light cone, essentially. And then the light cone is what represents basically the surface of the Big Bang. In this case here, the pass boundary of your spacetime is going to be this light cone. And then the extended spacetime is just this spacetime that's conformal to Minkowski space. And of course, we can only guarantee a continuous extension without any further regularity properties, right? So this is why we have just a continuous extension. But if you did assume further regularity properties, you can get C1, C2, et cetera, et cetera. Okay. Oh, and then maybe let me just make a point here. This vertex here, the origin, is going to play a special role in things to come. Okay. So just a quick comment on something. So note that this asymptotic assumption with the epsilon, it implies the same asymptotic assumption without the epsilon, right? And so then there are natural questions to ask. One, is it when you don't have the epsilon, is it sufficient? And the answer is no, there's not. And then you can ask, well, is it necessary? And then the answer is yes, it is necessary if you can show that if you assume that the limit of the derivative exists. And we don't know if this is going to be true or not, whether or not this condition holds. And then 3, right now, if you know that this part here, it's not sufficient without the epsilon, then you can ask with the epsilon, is it necessary? And the answer is no. You can find scale factors that satisfy A of tau equals tau plus the of tau, but not it with any epsilon. And the metric does extend continuously to the light cone. Okay, so lambda, the cosmological constant, appears as an initial condition. So let's see this. Okay, so FLRW spacetimes, they satisfy the Einstein equations with a perfect fluid. So this is a theorem. This isn't an assumption. So sometimes people like to say, suppose FLRW spacetimes satisfy the Einstein equations with a perfect fluid. You don't have to suppose this thing. This is just a true statement. And so what are these ingredients, right? So the Einstein equations are given by this, right? This is the stress energy form for a perfect fluid. Here U is just d by d tau, and then U star is the one form metric equivalent to it, and rho and p are defined as this, and then physically they represent the energy and pressure of the perfect fluid. But again, it's a theorem that this is true for these spacetimes where rho and p are given by this expression. Here K is 1, 0, or -1 depending on the space form. So if you were in the positively curved space, it was 1. If you're flat, it's 0, and then if you're in the hyperbolic case like Milne, then you're in -1. And then irregardless of the value of k, the equations for rho and p imply Freeman's second equation, which is given by this expression. So this equation here, which is basically just the Ray-Scheider equation, holds for all of these cases, k plus 1, 0, or minus 1. Okay. So to close the Einstein equations, so I haven't said anything about the equation of state yet. Well, what I'm saying is that if you took any FLRW spacetime, just any warp product, spacetime with these constant sectional curvature, you're going to satisfy this equation here. Any FLRW spacetime will satisfy this equation. And I'm not assuming anything. Yeah, so I'll leave it unspecified. So for any scale factor that you give me, then the Einstein equations will be satisfied with this. Yeah, exactly. It was just, yeah. I mean, the physics is going to come in the next slide when you do the equations of state. But this is something that I get into, yeah. But this is just something that, yeah. So I mean, it's just rho and p are defined through the scale factor essentially. Okay, so to close the Einstein equations, one imposes an equation of state, and this is just a relationship between rho and p, and it's usually determined via thermodynamic principles. So physically important equations of state are dust and then radiation. So dust is when the pressure is 0, and then radiation is when the pressure is 1/3 the energy density. And what's important is that both of these equations of state imply that the second derivative of the scale factor is negative, and this can be seen very easily from just plugging these things into Freeman's second equation here, okay? But the interesting thing is that observations show that the scale factor is accelerating, right? So the thing that we see as physical is not the thing that we observe. This is the point, right? And so to explain this effect, we introduced a cosmological constant into the Einstein equations, and we call it dark energy or so. And the important thing is that the equation of state for cosmological constant is where the pressure is equal to minus the energy density, which is related back to the constant itself, like this, right? So the equation of state for a cosmological constant is one where rho is equal to minus p, and you can see if you plug that into the Freeman equation, then the scale factor will accelerate. Okay. So how does the cosmological constant appear as an initial condition for Milne-like spacetimes? Well, this is not too hard to see, right? For simplicity, just assume that the scale factor has an analytic expression for right now, right? Then it's just a proposition. If C2 is equal to 0 in this expansion, then rho of 0 is equal to minus p of 0, right? And this is true for any, and then you can relate rho and p back to C3 as such. I mean, the thing that's interesting is that you didn't get back pressure, or you didn't get back dust, you didn't get back radiation. You got back exactly the equation of state that corresponds to the cosmological constant, right? And so this was the thing. I mean, this isn't a hard proposition to prove. You just plug this into the Freeman equations and it pops out. But the question was like, well, why does this happen? This was the thing that I was interested in. I think that there was something more happening here. Okay, so let me give the main result. Lambda appears as an initial condition because of the geometry of Milne-like spacetimes, and it's really going to be because of the geometry of the light cone that represents the boundary of the extension. Okay, so the motivation here is to generalize the previous proposition to spacetimes which share similar geometrical properties with Milne-like spacetimes, but we're not going to assume any isotropic or homogeneous assumptions. Okay, but we do want to keep some things. So what we want to keep are that they should solve the Einstein equations with the perfect fluid. So we're just going to make this assumption that the Einstein equations are satisfied with the perfect fluid. And we're going to assume that the co-moving observers, so we have a perfect fluid, so we have this vector field U. I define the co-moving observers as the integral curves of this vector field. We're going to assume that the co-moving observers for Milne-like spacetime, the co-moving observers are going to emanate from a single point, right? And the point is that this generalizes what happens in Milne-like spacetimes. In Milne-like spacetimes, if you took the co-moving observers, what you would find is that they all come out from this point, right? And this yeah, Stacey?
This is dependent upon a priori embedding into, otherwise there's no point.
Yeah, so we're assuming an extension. Yeah, we will. Yeah, that'll appear in the theorem. So yeah, the co-moving observers, they all emanate from this point, and this isn't a hard thing to see because the co-moving observers are orthogonal to the hyperboloids, right? And so imagine a hyperboloid here, and then those lines are going to be orthogonal to it, right? Lorentzian orthogonality, not Riemannian orthogonality. Okay, so here is the setting. Consider a continuous extension of a smooth spacetime, mg, such that m is equal to the time-like future of a special point O, right? This was what happens in Milne-like spacetimes. And we're going to call this O the origin. And this is supposed to be a point on the path boundary. Okay, so now a couple of definitions. Let f be a smooth function on your physical spacetime m. We say f is going to extend continuously to the origin, provided you can find a continuous function that extends it, right? So if you can find a C0 function on M union the origin such that its restriction to M is equal to F, then we say it extends continuously, right? And here, of course, the topology on M union O is just the subspace topology inherited from the extended spacetime. All right, more generally, consider any C infinity tensor field. We say T extends continuously to the origin, provided you can find a coordinate neighborhood U of the origin such that all the components of T within this neighborhood and within this neighborhood intersected your spacetime extend continuously to the origin. And this is something that doesn't depend on the coordinate system that you chose with by the usual transformation law for tensor components. Okay, so here is the theorem. So suppose you have a continuous extension of a smooth spacetime such that your spacetime was just the time-like future of a point for some special point, the origin on the path boundary, and assume that mg solves the Einstein equations with a perfect fluid. The integral curves of U, assume also that the integral curves of U have a path endpoint O, and a technical assumption, we're going to assume that when you extend this to O, that they're still time-like. This means that given your definition of time-like curves, whatever it is, that's satisfied, and also you have the local Lipschitz condition, right? This is a problem with defining time-like curves in low regularity, is what I'm saying. So whatever your definition is, make sure it's satisfied. Ricci, rho, and P, we're going to assume extend continuously to the origin. And we have to make a causal theory assumption that the extended spacetime is strongly causal at the origin. And in this case, the continuous extensions of rho and P satisfy this equation of state at the origin. So rho is equal to minus P precisely at the origin. And this is, right, this is precisely the equation of state of the cosmological constant. Okay. So let me prove this. Proof is by contradiction. So suppose rho does not equal P at the origin. Then let's take a look at the Einstein equations. We're assuming that they're solved for a perfect fluid, right? So we're assuming Ricci extends continuously. So then therefore the scalar curvature extends continuously. So then that means that the tensor T, the stress energy tensor, is going to extend continuously as well, right? So if rho plus P doesn't equal 0, then in a neighborhood, I can write this tensor U star like this, right? And since rho doesn't equal minus P, this will extend continuously, right? Because the right-hand side extends continuously, so therefore the left-hand side does. But then if this extends continuously, then you can prove that the one form extends continuously, and then of course then the vector field itself extends continuously to the origin. So this vector field extends continuously. Okay, now from here at this picture, this is where you should get the intuition, right? That vector field is not going to extend continuously because it's clearly not going to extend continuously, right? Okay, but then to prove it, you need some assumptions. So these assumptions, the integral curves of U have path endpoint O, M is the time-like future, and strong causality are going to imply that U does not extend continuously to the origin. And so this is a contradiction. Okay, and normally I would end the proof here, but because people here actually know causal theory and stuff, right, then I can actually do the proof of the causal theory part, so I'm going to do it. Okay. Right, so why do these assumptions imply that U does not extend continuously to the origin? I'm very intimidated by this water, so I'm hoping I don't have to use it. right? So the point is that you have a special point, right? The origin. And then what we're going to do is we're going to, right, from here, we know that u extends continuously to the origin. So then we're going to pick a small neighborhood around the origin, right? And the first thing we're going to do is that within this neighborhood, the metric components are very close to the Minkowski components. So you can always do this by continuity, right? And then moreover, u was a unit future-directed time-like vector, so it's going to extend to a unit future-directed time-like vector. So then using Graham-Schmidt accordingly, you can assume that that vector u is like this, right? So the other assumption is that u, the extension, u at this point is equal to partial like 0 at this point. Okay, and then because u extends continuously, you know that the components of u are not too different from partial like 0, right? So the point is that u tilde, well, the difference between u0 and -1 is smaller than epsilon because it's basically that, and then also ui -1 is smaller than epsilon. Okay, so it should look, this vector field should look very much like this vector field here. Okay, but then now, since m is equal to the time-like future of this point, right, you know that the time-like future is going to be maybe something like this. So maybe it'll be over here. So I'm going to take a point Q, and if it's sufficiently within the light cone, you know that this is going to be part of your original spacetime. Mm-hmm. Oh, this one, yeah, this should be 0. Got it? Yeah. Mm-hmm. Okay, and then, so then now you look at the integral curves of u through this vector field, and by this assumption here, we know that they have passed endpoint O. So you know that the integral curve of u, in a different color, has to look maybe something like this, right? But then the point is that by the mean value theorem, you know that at some point the derivative here is going to be pretty long. Remember, this still has to be a unit time-like thing. And then clearly this is going to be a problem. This vector here and this vector are very far away from each other, but they had to be close to each other. This is the contradiction. Okay, but I still haven't used strong causality, so how does that get into play? So you have to make sure that this integral curve u was inside this neighborhood, right? The thing you have to be worried about is that it might leave the neighborhood and come back, and then everything inside the neighborhood, it would look like partial like 0. So then you use strong causality, and that forces the integral curve to be within the neighborhood. Okay, so that was the proof. Okay, so let me make a remark. The main theorem remains true with strong causality replaced by this assumption here. For any neighborhood u of the origin, there's a neighborhood v inside u, such that the pass boundary of m within v lies in the time-like future of O within u. And so basically, you know, if you didn't want to assume strong causality, you could have assumed this. And the proof of this uses the fact that the pass boundary is an achronal topological hypersurface whenever the future boundary is empty, and the future boundary is empty because we're assuming that the spacetime was equal to the time-like future of the extended thing. So you can show that the future boundary is empty there. And I think it's interesting that, you know, this assumption here, it sort of sounds like strong causality in a way. For every neighborhood u, there's another neighborhood such that the one neighborhood v does something else in that other neighborhood, right? Okay, so now let me say a little about the applications to inflationary theory. So many cosmologists argue that the scale factor underwent an inflationary era after the Big Bang, but before the radiation-dominated era. So maybe let me just say a little bit about this. So let me graph the scale factor as a function of time tau, right? And basically the point is that physicists are pretty confident about what happened after like 1 second after the Big Bang. And it's not that they know exactly when 1 second after the Big Bang was, it's just that we know the temperatures. You know, we can correlate time to temperature, and we know the physics of the temperatures at this. So that's what we mean 1 second, right? And so after that, basically we know that the scale factor was in a radiation-dominated era and then a matter-dominated era, right? And then eventually dark energy kicked in, and now it's accelerating. So this picture we're pretty confident in, right? This is stuff that we observe and we're good with. What happens between here and tau equals 0, this is where we're less confident about, right? And so if you don't believe in inflationary theory, then you would make the assumption that, well, I probably think that it should have been a radiation-dominated era all the way to the Big Bang, and so then I'm going to assume something like that. If you want to make that assumption, this doesn't agree with Milne-like spacetime. So you couldn't do this thing with Milne if you make the assumption with a radiation-dominated era. And so, but if you do assume an inflationary era, then so if you assume inflation, then that would look something like this. So it's inflation, so it's accelerating, and then at some point, what physicists call reheating kicks in, and then it turns into a radiation-dominated era. Okay, so the point is that we just don't know what happens. So if you believe in inflation, this is the picture, and this is consistent with Milne-like spacetimes. The radiation-dominated era is not consistent with Milne-like spacetimes. Okay. So, whoops. Okay, so physicists believe that something like an inflationary era occurred, right? Recall Freeman's second equation is given by this. So therefore, if rho of 0 was equal to minus p at 0, and the pressure and the energy density was positive, that would imply that the scale factor is accelerating, right? You just plug that into the Freeman equations, and physicists call this a quasi de Sitter expansion for the early universe. And so the point is that the main theorem can be used to generalize this type of quasi de Sitter expansion to spacetimes, but without assuming any of these homogeneous or isotropic assumptions. Okay, so how do we do that? So for FLRW spacetimes, Freeman's second equation can be written like this. Now, for arbitrary spacetimes with a unit time-like vector field U, the generalization of Freeman's second equation is just the Raychaud-Durry equation. And so here, this is the Raychaud-Durry equation. This math frac A is defined via A dot over A is equal to H, where H is equal to 1/3 the divergence of U. If U is hypersurface orthogonal, then this would just be the mean curvature, right? And then also H, this is the same letter as this is also the same as the Hubble parameter. So it's nice that the mean curvature and the Hubble parameter use the same letter. Okay, so here, this math frac A, it generalizes the scale factor. H generalizes the Hubble parameter. Tau is just the flow parameter of U. This is the proper time. And omega and sigma are these vorticity and shear scalars, and they only depend on the spatial part of U. Okay. So now, if mg solves the Einstein equations with a perfect fluid, then we can rewrite the Einstein equations as such, right? So this is just Ricci in terms of these quantities. Now, a corollary of our main theorem is that the Ricci tensor at O is equal to a pi rho times the metric. So it kind of looks like an Einstein manifold, but right at the origin. So it's not Einstein everywhere, it's just right at the origin, it's Einstein. If rho equals minus p, this term dies and this term dies, and so that's how you can get this expression. But the point is that if you're sufficiently close to the origin, then Ricci of UU is going to be like this, right? You just plug that into here. And so if you insert this into the Raychaud-Durry equation, you get this expression. Now let's just make some simplifying assumptions. Suppose U is hypersurface orthogonal, so the vorticity vanishes, and assume U is a geodesic vector field, so this term vanishes, right? So this is what happens in FLRW. Then this is the Raychaud-Durry equation. And so we see here that if sigma squared is small, then this yields a generalization of an inflationary era if you assume that rho is positive, rho of 0 is positive. So sigma, of course, is 0 for FLRW spacetimes, right? So in some sense, you get a nice generalization of these quasi de Sitter expansions if you assume that the shear is small. Okay, so now let me talk about some upcoming work with Gazelle, Gesni, Sujanani, and Jerome Quinton on past asymptotically flat de Sitter spacetimes. And the point is that everything that I just said that was true for Milne-like spacetimes is also going to hold for these flat de Sitter models. Okay, so consider a flat k equals 0 FLRW spacetime. And so here is the manifold, and this is the metric that we're assuming, right? So we're assuming flat now. We're not assuming the hyperbolic metric. if I equals R and A of tau has this exponential form for some positive H, then we're going to call MG a flat de Sitter spacetime, and that's just because it's locally isometric to de Sitter space. Okay, but the point is that flat de Sitter spacetimes, they conformally embed into the Einstein static universe, right? So this picture here, the Einstein static universe is represented by the Einstein cylinder, right? Chi is the angular variable on S3, right? Going from the North Pole to the South Pole. T prime goes from minus infinity to plus infinity. The de Sitter spacetime conformally embeds into this, and it's given by this whole square here from minus pi over 2 to pi over 2. At pi over 2, that would be scri plus, and at minus pi over 2, that would be scri minus. So that would be the full de Sitter space, the one where you have all of S3 or so, right? But this part right here, where you just take the k equals 0 part, you only get half of de Sitter space, right? So in this case, you just get basically what's on the left half of this square. It's not really a square, right? This variable from chi equals 0 to pi, this is an angular variable on S3, right? And so what's interesting is that, again, in this spacetime, the co-moving observers are given by these red lines. And what you see is that the co-moving observers, they all terminate at this point here. And this point here represents the North Pole on S3 at t prime equals minus pi over 2. So they actually limit to a point and not like a sphere or something. So that just takes some work to show. So again, we're kind of seeing a very similar picture that we saw with Milne-like spacetimes, right? Again, the spacetime that you're interested in is the time-like future of something where everything is emanating from a single point. But the difference with Milne-like spacetimes is that this point here is not a point on the extended spacetime, but it's a point on a conformal extension, right? Everything at minus pi over 2, everything right here was on scri minus, right? So you have to be careful. Okay. So a little more generally, suppose that your interval goes from minus infinity to tau max, and h of tau goes to some positive number h, where h is the Hubble parameter or mean curvature or so. Then we call mg past asymptotically flat de Sitter. And basically, the past asymptotically flat de Sitter spacetimes, if you satisfy this assumption that the Hubble parameter just goes to a constant, then you're going to get the exact same, this picture is going to also hold essentially for these models. So it's not something that was restricted to just pure asymptotic or just pure de Sitter. Also works with asymptotic de Sitter. Okay, so to capture these effects, we created a new definition. So suppose mg is a smooth spacetime and m tilde g tilde is a C0 spacetime. We call m tilde g tilde a C0 conformal extension, and we haven't put this on the archive yet, so if someone finds a better name for this, please tell me, because I don't even know if this is what I should be calling this. So we call it a C0 conformal extension of mg if there's an embedding m into m tilde and a continuous function omega from the closure of m into 0 infinity, such that m inside m tilde is a proper subset, omega restricted to m is positive. This conformal boundary is non-empty, where I'm defining this conformal boundary to be the set of points on the boundary where omega p is equal to 0, and the pullback of g tilde under the embedding is equal to omega squared g is a conformal embedding, right? We defined the future and past conformal boundaries analogously, so the future conformal boundary would be the points p on the conformal boundary where you can find a terminating time-like curve, and analogously for the past. So in this de Sitter case, this point right here, right? So here, what's happening? This would correspond to the future conformal boundary points, but there's only one single point here that corresponds to the past conformal boundary. So in this case, for these spacetimes, the past conformal boundary is precisely just that point on scri minus, right? Of course, the boundary still contains this light cone. You still extend through this. It's in this exact same way. You can think of this surface as like the surface of the Big Bang, maybe, right? But it extends, I mean, not Big Bang because it's t equals minus infinity, but it's where the scale factor goes to 0. And so so you still extend through this, but this isn't part of the conformal boundary, right? Omega is not equal to 0 over here. Okay. Again, the Freeman equations, they imply that the Hubble parameter is equal to minus 4 pi. So for this k equals 0, the Freeman equations can be written like this. Now, if h approaches a constant, then it's natural to assume that the derivative of h goes to 0. So if the derivative of h goes to 0, then once again, you're seeing that rho is equal to minus p, right? So convergence of h and h dot is going to imply convergence of rho and p. This isn't too hard to see, it follows from the Freeman equations. Hence, if h dot goes to 0, you're going to find that rho of minus infinity is equal to minus p of minus infinity. So again, this equation of state mimicking a cosmological constant is showing up. So this is the analogous theorem. This is the analogous theorem of the one for Milne-like spacetime. So now m tilde g tilde is a C0 conformal extension of mg with a conformal factor omega such that m is equal to the time-like future. For technical reasons, we had to say that it's intersected with m itself because you can see why that doesn't hold for the Einstein static universe. So now for some point, and assume this is true, for some point O on the past conformal boundary, assume mg solves the Einstein equations for the perfect fluid. Each of the integral curves U have passed endpoint O, and they're time-like, rho, p, and now instead of Ricci extending continuously, you need to assume omega squared Ricci extends continuously. So this is kind of something that's interesting because Ricci won't extend continuously, but omega squared Ricci does. And for the cases of the past asymptotically de Sitter spacetimes, we saw that this was a reasonable assumption. So there are natural assumptions that make this actually extend continuously to the origin. Finally, assume that m tilde g tilde is strongly causal at the origin. Then the continuous extension of rho and p will be rho tilde is equal to minus p tilde at the origin. And again, the continuous extension of omega squared Ricci g at the origin is equal to 8 pi rho tilde g tilde at the origin, right? So let me just make one point at this. I don't want to use the water. So omega squared Ricci, right, g tilde is equal to, so this is a true statement at that origin that lies on the past conformal boundary, okay? But this is equal to 8 pi rho tilde g tilde. But if you're at a point that's not on the past conformal boundary, so let's say this was your single point on the past conformal boundary, but let's say you're in a small neighborhood, let's say you're right there, right close to it, but you're still in the space-time you're considering, then this conformal metric is just equal to omega squared g, right? By definition of a conformal. So then now this cancels, and so then you can do the exact same thing that you did with the Ricci-Durry equation before to get a natural generalization of an inflationary era. So again, you have the exact same application to inflationary theory that you had for Milne-like spacetimes. Okay, so here are some future directions. Are there spacetimes that satisfy the hypotheses of the main theorem but are not Milne-like? And likewise with the past asymptotically flat de Sitter case. So I make this big old spiel, right? I'm doing this for non-homogeneous, non-isotropic spacetimes, but I haven't actually found one that is not a Milne-like or not exactly de Sitter, right? So I need to find one before I can say anything great. Okay, somewhat related to this is a possible initial value problem from the origin. And then finally, so Gazelle, she's more interested in bouncing cosmologies. So this is something like de Sitter spacetime, right? De Sitter is something that bounces. And so the question that we want to ask is, well, you take this flat de Sitter model and you time invert that and you put that on the right-hand side and you glue them together. And then in what cases is that going to produce something that gives you a bouncing cosmology, right? Okay, and I think that's it. Thank you.